almost every single problem. So I'm going to show you what we're doing. We're going to start doing all of these rules, and we're really going to deal with briefly, very minimal, the definition of the derivative for the rest of the year. We're mostly just going to, take the derivative and use it for applications and things. But I don't want you to lose track of what we're doing. We're still doing what a derivative is. It's an instantaneous rate of change of a function. And you're just finding the value of a function, the rate of change of that function at a point, or the slope of the tangent line. And that's what we're going to do the whole first semester, is take these derivatives. So let's take a look at some rules. So I did the rule with what we've done so far in each of these different rules. For example, the first one is if you have a constant, df dx, or the derivative, this is what I mean by d here, is the change in the function value over change in x, or the change in y over change in x, is equal to d dx of the function. This is still the same thing. It's the change in the function over change in x. If you're looking at a constant, like f of x equals 2, that's a constant line. What's the rate of change of any constant? 0. I mean, you can graph it, and then you can do change in y over change in x if you want, but the rate of change everywhere for any constant number, is 0. So the derivative, f prime, or df dx or d dx of that constant is going to be 0. Any questions on that? Is that yes or no? No. Okay, good. Now, all right. The second rule is a power rule. And again, it's for any polynomial. When you have x raised to a value, and that value is an integer, you use the power rule. d dx of x to the n, meaning x raised to some integer, is equal to taking that number, moving it down here, and then subtracting 1 from the value. And this is what we've been doing. For x squared, for example, if you go through your whole process of change in y over change in x, again, the limit as h approaches 0. You get your 2 points, really close to each other, x and x squared, x plus h, and then this whole thing multiplied out. If you do your change in y over change in x through the whole process, you get to here, dump in 0 for h, and you get 2x. Using the rule, you take the 2, you put it down here, and then you subtract 1 from here. You get 2x to the 1, or just 2x. Does that make sense, guys? So what that means is the derivative, and what this is a function. You've created a function that now you can plug in any x value to figure out what the rate of change is for this function. Does that make sense what we did, guys? You've created a function itself. The derivative is a function where you can plug in x values to find the rates of change at any x values of the original function. Yes, Amina?
Why does that work?
Why is what?
Why does that work?
We've been doing this. You know what I'm saying?
Yeah. No, I understand the old way. I just don't understand why.
So what they did back in the day is they kept on doing these, and they noticed the patterns. They did an x cubed, and then they did 5x cubed, and then they did x to the 4, and they did all of the longhand way, and they kept on coming back. Like this is a proof for x squared. Like if you go through, you do your change in y over change in x. For x squared, you get 2x. If you do it, this is what we're doing. What someone just said is, you know what? After doing 100 of these, it's the same thing. It's always this number comes down, and then you subtract 1 from here. And the proofs, this is our pudding. It's in here. You know what I'm saying? And this is what you can do every single function for. And if you don't like the rules, you can always go back and do this. You know what I'm saying? Or use the rule. But what the rule is, again, it's a strategy to not do this every time. But, Estella, this is what you're doing every single time. If you want to find the rate of change of a function, you're finding the change in y over change in x for a very small interval on a specific function. The rules are just so you don't have to do this every time. Okay? Yes?
Will there ever be a time, like on a test or on the AP test, where you have to write it out, like the first?
Maybe, definitely on quizzes. If I ask for the definition of the derivative, use the definition of the derivative to calculate, and it will come up, because I saw a lot of people on the test still didn't know how to use this process. They would do all the algebra. They would get to here, and then not know what to do here because this limit wasn't written there. You didn't know what you were doing the entire time. You did all the hard work, and it was just kind of like, okay, I did the stuff that you wanted me to do, Mr. Remus. But like, what are we doing? You're finding the change in y over change in x for a small interval. Okay? But the good thing about derivatives, with these rules that we're going to learn, you can literally take the derivative of any function I can ever throw at you. Ever. You can take the derivative of using these rules. Anything I can ever throw at you. So, what if I stick a 5 in front of that x squared? So x squared, what's the derivative of x squared? 2x. Well, what's the derivative of 5x squared there? If there's a number stuck to the x squared, it's multiplied by it. Well, yeah, you can go through the same process. I mean, you check it out. Go through the whole thing, you know what I'm saying? And keep on doing it. Continue to do it if you don't believe it, you know what I'm saying? Well, people spent centuries working on this stuff. For you, so you have it. You know what I'm saying? So you don't have to do this every time. You can work on more applications and more, like, you know, all these other different things we're going to do. But if you have 5x squared, you can do the same thing. X and x plus h, 2 points really close to each other. The change in y over change in x. You can multiply it all out. And then you'll get to this, and then you plug in h as 0, and you get 10x. And then you do that 100 times. You change the numbers, and then say, I've noticed a pattern. And that pattern is, if you have a constant times the function, then the derivative is going to be that value just kind of stuck to the derivative of the function. For example, in this case, 5x squared, well, if you just kind of ignore the 5 for now, you take the derivative of x squared, which is you bring the 2 down, and then x, and then you subtract 1, and then you multiply the 5 by it. And you get the same thing every time. So again, you can use the old way we've been doing. This works. You can do it every single time. Or you can use your trick and just move on. So what about the function 7x cubed? What's the derivative? If I wanted to know that the rate of change at some specific spot for 7x cubed. Yeah, okay. So like here's what we're doing. Alright? Marco, you know, we're doing all this stuff, and it's like, okay, here's 7x cubed. And I want to know the equation of the tangent line at x equals 1. Okay? What can you do in order to answer my question? How can you answer my question? What is the equation of the tangent line for 7x cubed at x equals 1? How fast is this thing changing? What's the rate of change of this function for an x value of 1? What was the first thing you guys can do? Yeah, you can take the derivative. What I'm going to do first, and what I always do first if I'm solving for a tangent line, Joanna, I know I need 2 things, a point and a slope. You know what I'm saying? Because then I dump it directly into point slope. Because I never, ever do y equals mx plus b anymore. Because that would be weird. Ever. Point slope. Because you're going to make a mistake solving for b, which people did on the test. First thing I do is solve for a point, because that's the easiest. What is a point on this graph? What is the point? At x is 1, what's the point? 1, 7. At an x value of 1, this function has a y value of 7. I do that first so you don't plug in something into something you shouldn't plug it into. So I have a point. The only other thing I need is a what, Chris? I need a slope. How can I figure out what the slope is of this function at that point? Cricket. Cricket. You take the derivative. Yeah, I mean, you use what we're doing. Like, you can either do the whole thing with this x cubed, which is going to be a big mess, or take the derivative, and you get what?
21x squared.
So is this the slope, 21x squared?
No, it's 21.
No, like, what is this?
It's a function for the derivative.
Yeah, it's a function that can give you the slope for any x value you want.